Yes, you're
Oh,
recording.
hello everyone, and welcome to the and greetings from the sunny Bergen, and welcome to the seminar from TS of Parameterized Complexity. I'm very happy to introduce our speaker of the day, William Lochet, who will speak about nice problem about disjoint path problems. Welcome, William.
Okay, so thank you very much, Fedor, for the introduction and the invitation. So today I'm going to present you a polynomial time algorithm for the k-disjoint shortest path problem. And so before talking about the disjoint shortest path problem, let's start with the very classical disjoint path problem. So the setting is the following. You have a graph G. So for the moment, it's undirected. We'll talk a bit about the directed case later. Some set of k vertices S1, Sk, and then another set of k vertices T1, Tk. And then the very natural question that appears in many settings is, can you find a set of disjoint paths linking S and T? Okay. So if you don't have any constraint on the extremity of these paths, then this is a very classical flow problem, and then you have a very efficient polynomial time algorithm. But if you ask that each path, so for each pi links Si to Ti, so for example, here you have a path linking S1 to T1, then this is the famous k-disjoint path problem, and it becomes NP hard. So this is one of the most studied problems in algorithmic graph theory. And then there is this very famous Robertson and Seymour theorem from 1995, which says that the k-disjoint path problem is FPT, and actually there is a cubic algorithm. Okay, so this is a very complicated algorithm using a lot of the theory from the graph minor project. But it's also very important in this project because it allowed to decide for the existence of a minor, a fixed minor H in G. So this is the same algorithm, basically. And since then, it has been extensively studied. So to get a better algorithm, to understand it a bit better, to get better complexity and other stuff like that. So this is for the undirected case. It's pretty well known, pretty well understood, and it's a pretty nice result. And so before going to the problem that we're interested in, let me just mention the directed version of this problem. So it's exactly the same question, but instead of having an undirected graph, you have a directed graph. And in the directed case, everything is much harder. And actually, and this is a very famous theorem from Partition et al. From the 80s, which shows that the two disjoint path problem on directed graph is NP hard. Okay, so yeah, even for two, it's not possible to get a polynomial time algorithm. But nevertheless, it has been studied in many classes. And then there is one particular class which would be very interesting for us that I want to mention is the class of DAG, so acyclic digraph. And on this class of graph, then we know that there is an n to the big O of k algorithm. Okay, so XP. So this is in the same paper by Fortune et al. But we also know, and this is Flickins from 2010, that the problem W1 half. So yeah, so that's the picture, and so here the theorem of Robertson and Seymour tells us, okay, there is an algorithm to decide if you can link these points, and a very natural question that comes after the Robertson and Seymour algorithm is the following: is okay, so we can find a solution. Can we find the best one? And what I mean is, like, can we find one which minimizes, let's say, the sum of the paths, for example? So if you look at it from a minor point of view, it might not be super important, but if you look at it from like a flow problem or like a network problem, then this question makes like a lot of sense. And so these questions, okay, so people have thought about it, but actually we don't, there is very, the knowledge that we have on this question is way, way less than compared to the normal one. So for the Robertson and Seymour algorithm. So this has been studied. So for example, for k equal to 2, there is an algorithm that dates back to 2015 by Bergen and Usfeld. This is a very nice algorithm, and it uses ideas which are completely different from the Robertson and Seymour algorithm, because this is a algebraic algorithm compared to the very tree widths and grid minors from Robertson and Seymour. It also has been studied in the planar case. So here, I think the study had been started by some paper by Schreiber and Colin de Verdière, where they look at, so in planar graph, this question in planar graph, and they look at the specific case where the points, so the SI and the TI, they all belong to one or two faces, okay? But basically, apart from these two, type of results, nothing is known. And in particular for the case k equal to 3, for example, I don't know anything about it. Even like approximation algorithm, I mean, nothing is known. So this seems like a very open question. And in fact, the following question also was open for a very long time. And this will be the question that interests us today. So the problem is the following. So you have a disjoint path instance, so a set of vertices SITI. And now you ask for the question of, can you find a solution to the disjoint path problem where every PI is the shortest path between SI and TI? Okay, so if you want to find a solution which minimizes the sum of the paths, then this is like the best solution possible. And the question that we ask is, can we find such an optimal solution? And here, this is obviously weaker than this question, because if you can find the optimal solution, then you can check if the sum of the lengths of the path is equal to the sum of the lengths of the shortest path between the SI and TI. Okay, so this is a weaker question, and even for that, we didn't know anything for k equal to 3 until the result that I'm presenting now. So this was a problem posed by Eilam-Tzoreff in 1998 during her PhD thesis. And in the same paper, she proved the case k equal to 2. So she proved that in the case k equal to 2, there is a polynomial time algorithm in undirected graph. And in the same paper, she asked the question for directed and undirected graph for any fixed k. Okay, and until the result that I'm presenting you now, the case k equal to 3 was also open. And then this is basically what we're going to see today. So this is a very old, I mean, this is a quite old question, but it has received some attention lately, particularly because of the following result by Terchi and Kobayashi, so 2017, which says that in the directed case, okay, so in the directed graph, the two disjoint shortest path problem admits a polynomial time algorithm. Okay, so this is in contrast to the normal disjoint path problem in that graph, which is NPR for k equal to 2, right? So here, and this is interesting, I mean, it's not very surprising, but when you're looking in directed graph and you restrict the space of the solution that you look for for shortest path, then the problem becomes easier. Okay, that's the natural statement I want to say, but we'll see that doesn't happen all the time. So this is quite a nice result, and then the proof is nice. And so since this paper, a lot of people have tried to study actually their results. Okay, and then let me just say also that in the same paper, they proved that the algorithm of Schrever for planar graph, for disjoint paths on planar graph, can be adapted to this setting. So shortest disjoint shortest path in planar graph also has a polynomial time algorithm for any fixed k. Okay. And this is what I said, that there has been a lot of papers coming out after this one studying like variation of it. So non-negative weights, also what happens if you ask for paths which are slightly longer and stuff like that. But this was basically just generalization of their result. Okay, and then so now the goal of the talk will be to present you the proof that I made. It was an archive last year, but it will appear next year, so 2021. That shows that the k-disjoint shortest path problem admits an n to the f of k algorithm, so an XP algorithm. And so the argument works for both edge and vertex, so edge disjoint and vertex disjoint version. So I didn't specify this in the presentation, but like it works for both. And the paper is written for vertex because it's hardest case, but the talk will focus on the edge disjoint version because it simplifies a bit some technicalities. Okay, and so the goal of the talk is basically to present you ideas for this algorithm. But before I go to that, there is the very natural question of, okay, so there is an XP algorithm. Can we find an FPT algorithm for this? And the answer is no. And actually, it's quite an easy reduction from disjoint path on that. Okay, so the theorem is that k disjoint shortest path, directed or not, is W1 hard. And here, before I present you the reduction, a small remark. As I said, in the case k equal to 2 in directed, looking for only shortest path makes the problem easier. I mean, because we have a polynomial algorithm and there is not in the general case. But here, this result tells you that in the undirected case, then this problem is harder. Okay, so something strange is happening, and then basically we'll see what exactly is happening. So But yeah, so what's the proof? Well, you start with your favorite instance on disjoint pass on a directed acyclic graph. Okay, so D and a set of SITI. And then you look at the topological order of this graph D. Okay, so when you have a graph which is acyclic, then we have a topological order, which is an order of the vertices V1, Vn, so that all the arcs go in the same direction. So here, for example, you have V1, V2, V3, and all the arcs, they go like this. So from the vertex with the smallest index to the vertex to the largest index. And then once you have your topological order, basically what we will do is we'll modify this graph so that every pass is the shortest path. Okay. So how we do this? Well, if you subdivide each arc, so let's say you have an arc between, so from Vi to Vj, then you will subdivide it j minus I minus 1 times. Okay. So this is what we do. So because, for example, here between V1 and V2, okay, so 2 minus 1 minus 1 is 0, so you don't subdivide it, but you had an arc from V1 to V3, so, and you subdivide it 1 time, and etc. Okay, so this works. And then, so what happened when you do this? So you have a new digraph with n square vertices, that's okay. And so basically what happened now is that every pass between, from Vi to Vj are lengths j minus I. Okay, so every pass has the same length, so every pass is the shortest path. Okay, so for example, between V1 and V3, well, you have 2 paths basically. So this one is length 2, and this one has also length 2. Okay, so every path is the shortest path. So if you can solve the disjoint shortest path in it, then you can solve disjoint path in the original problem. So this is for the directed case. And actually, if you forget about the orientation here, then the shortest path in this undirected graph will correspond to paths in the original directed graph. Okay. So very easy reduction that basically tells us that this problem is very much linked to the disjoint path on DAGs. Okay, and for this reason, it's W1 hard. Yeah, and for this reason, it's W1 hard. Okay, all right. So now that this is clear, that the W1 is clear, I will present you some ideas for the algorithm. Okay, and as we've seen. This problem is very close to the disjoint path on DAX problem, and then let me tell you the reason. Okay, so for the moment, from now on, we will have a set of like S1T1, S2T2, S3T3, and then we look for the shortest path between S1 and T1 and the shortest path between S2 and T2, etc. Okay, so to understand that and to design an algorithm, we need to understand the structure of the shortest path between S1 and T1. Okay, and fortunately for us, this is a very easy structure, and you see how DAGs appear, because if you start from S1 and you do a BFS from S1, so it defines some sort of levels, so L1, which is this one, L2, etc., until R. So this is a partition of the vertices of the graph, and now every shortest path starting from S1, it just follows the levels, right? So in particular, it means that the only edges that we care about are these edges, okay? And because we'll have like several paths, then basically we'll get several colors. So for the moment, we'll call these edges blue edges, okay? And actually, if you orient these edges between like 2 consecutive levels, so like this, so between 1 and 2, 2 and 3, etc., then actually what you're looking for is not a shortest path between S1 and T1 in the graph. You're looking for a directed path in this graph, okay? Directed path in this blue graph. And for now on, what we will call blue path will be a directed path in this graph, okay? So you do a BFS from S1, and it's defined you a partition of the vertices in 2 levels, and it defined you orientation of the edges between these things. And you have a directed graph, and you want to find a path in this directed graph, okay? And so here the remark is that this is a DAG, and this is basically where this the reduction comes from. I mean, we see this like DAGs appearing again. So yeah, so if you start from S1 and you do BFS, it gives you 1 color, and obviously since you want a shortest path from S2 to T2, what you will do is you will do another BFS from S2. So this gives you another partition of the vertices, it gives you another color basically, and this is what we call the red color. Okay, so you want a blue path from S1 to T1 and a red path from S2 to T2, and you want them to be both disjoint. Let's say if we keep to 2 paths. Okay, And here the remark that we have is that one edge can be of both colors. Okay, and actually, if it doesn't happen, then everything is very easy. And another remark is that the orientation of one edge, can be different in both colors. So this is fine. All right, and so now we defined what we call the k-colored graph. Okay, so it's basically a graph G and k partition of the vertices. So this gives you k colors, and then all of these colors are obtained by doing one BFS, right? So I don't want to go into too much details, but just you start with a graph G, and then you do k BFS, and it gives you k colors. So this is fine. And actually what it allows us to do is it allows us to generalize a bit the result that we're trying to prove. So because before we had like k points, and then we do k BFS, and then we want one path in each color. But actually we can ask for more than one path in each color. So I don't want to read this, but basically the idea is that you have a graph G. Let's say you do two BFS, so it gives you two colors, red and blue, and then you want one red pass between S1 and T1, one red pass between S2 and T2, and one red pass between S2 and T3. Okay, so you ask for more than one pass in each color, but this is fine. And this is a generalization in the sense that we will prove that the problem here, so solving this problem is doable in polynomial time. And here there is a dependency in K and L. All right. Okay, and then why do we do this? Well, basically, we do this because we want to stress out that the hard part of this problem doesn't come from the number of paths, but it comes from the number of colors. Okay. So what I mean by that is that look at the case k equal to 1, for example. So suppose you have just one color. So what does it mean? It means you start from one vertex, you do one BFS, you get a directed acyclic graph, and now you want disjoint paths in the directed acyclic graph. Okay, so you had like S1T1, S2T2. Okay, so the case k equal to 1, it's equivalent to the case of disjoint paths in the directed acyclic graph. And as we've seen, this is the fortunate algorithm. The L disjoint paths, okay, so L is the number of paths and K is the number of colors, so we have to be careful here. So the L disjoint paths on DAGs admits the n to the big O of L algorithm. Okay, so it means that for one color, we know how to do it. Okay, and we know how to do it for any n, right? So basically, the idea will be to try to reduce the number of colors we're considering by possibly augmenting the number of paths we have to deal with. Okay, but when k equal to 1, we can do as much paths as we want. And in fact, if you remember the hardness proof, this was already for the case when k equal to 1. Okay, so case k equal to 1, so we know how to do it, but it already contains all the Boolean hardness of it. All right, so we have the case k equal to 1, and now the question is, how do we go from 2 to 1? Okay. So the algorithm basically will be a generalization of fortunate algorithm for DAGs. So probably many of you have seen it. So for a lot of people, it's basically dynamic programming. Okay, so they don't present it the same way. Also in the paper, I don't, because I find it a bit more nice. But okay, that's the only thing I will tell about it. It's like it's a very nice but very simple algorithm. And what we do here is generalize this algorithm. But before generalize this algorithm, we have to work a bit. And basically, we have to show some properties of a solution, of a possible solution. Okay. And so the main idea of the proof will be to show that, okay, given an instant of this problem, so KL DSP problem, you want to find some intermediate points on the solution so that paths of different colors cannot intersect. Right. So what I mean by that is, so you start with the previous instance. So you have S1T1, S2T2, and S3T3. Okay, you want one red, and one blue path. And now you say, okay, maybe I will try to guess some of the points in the middle. So like this one, this one, this one, this one, and this one. So that now, basically, if I guess this point, then I have to find a path from here to here, a path from here to here, and a path from here to here. So I have more paths to find. But the trade-off here will be that now we want that two paths of different colors cannot intersect. So what I mean is that if I look at these two constraints, so a red path from here to here and a blue path from here to here, then there is no red path from here to here that can intersect a blue path from here to here. Okay, so if you find these middle points, basically you want to reduce the space of all possible paths that you're looking for, so that now you don't have any conflict between different colors. And if this is the case, then morally you want to apply fortunate algorithm for each color separately. And then since you know that they won't intersect anyway, then you just have to do this. Okay, so that's really the main idea. But I mean, we won't do it exactly the way I say, but that's really the main point. So guessing intermediate points, so that now you don't have any conflict between different colors. And once you don't have any conflict between different colors, you can just apply fortunate algorithm for that. Right. Okay. So that's the point. All right. So, okay, how do we find these points? And actually what we will do is we'll show that these points exist. Okay, and if they exist and they're finite, then you can just try all of them. Okay, so now the things we have to do is to show that the existence of these points. Okay, and I'll be a bit more clear about what I mean by all these properties, but this is just a general idea. Okay, and so to prove that these points exist, we have to understand how can two paths can intersect. How can a blue path and a red path intersect? Is there nice properties for this possible intersection? And the answer is yes. So really what we have to understand is the sets of B-colored edges. Okay, so edges which appear in both BFS, basically. So for that, we will define two graphs. So the one I call G plus and the one I call G minus. So G plus is the graph of all the edges which are blue and red. Okay, so for the moment, I just stick to two colors. And they have the same orientation. Okay, so meaning that you use them in the same way to go from S1 to T1 or to go from S2 to T2. Okay, and G minus is just, okay, the same thing. So the graph of blue edges, but the orientation are reversed. Okay, so they're not used in the same way. And so what we call a B-colored component now is just a connected component of either G plus or G minus. Okay. All right. Okay, so this is the B-colored component, and so let me give a few remarks about them. The first remark is that this is the main ingredient in already the Berchi and Kobayashi's proof for the case k equal to 2 in directed case. Okay, yes. And also there is another remark that I have to make now, which will allow us to forget about G minus, is that if you look at G plus and G minus, so there are two different graphs, okay, so you have two different set of components, but actually they play exactly the same role. Because, I mean, the orientation, it's basically how you go from SI to TI, okay? So this is the orientation, let's say, if you want to go from S1 to T1, this is the orientation that you give to the blue edges, okay? So how you go from S1 to T1. But like, I mean, S1, T1, they play exactly the same. I mean, they have a symmetrical role. So you can reverse these two, and then by doing this, you just transform G plus into G minus, right? So these two graphs exist, and you have to understand both of them together. But like, if you want to find if you have just one B-colored component, then you can think of it as a component of G plus because it doesn't matter, okay? Especially for indices, it would be a bit easier. All right, so for the moment, so from now on, we only think about G plus when we talk about this component. And the first lemma that I really want to explain here is the following one. It said that suppose that P is a blue path, so it's the shortest path in the blue component, and CI is a B-colored component, let's say blue and red. Then the intersection of P and CI is a subpath. Okay, so these components, they play nicely with these paths that we're looking for, right? So they intersect them on a subpath. Okay, and so I have to prove this. And as I said, the component CI, we can take it in G plus, right? Because worst case, we just reverse. All right. Okay, so let's prove this. So first, let me make a small remark about so these components, especially the component of G plus. So if C is a component of G plus, then basically what it means that the two BFS on this component induce the same partition. Okay. So what I mean by that, I mean that for every 2 versus U and V in this component, then the difference of levels are the same in both columns. Okay. So for example, you have U and you have V, and let's say the difference of levels is 2. So U is in the first and V is in the third, for example. In the blue levels, then what I claim is that it will be the same for the red levels. Okay, so maybe not 1 and 3, but like I and I plus 2. Okay, and the way we see this is that okay, so C is a connected component, okay, of blue and red edges. So, but now if you take a path from U to V, okay, a blue path from U to V, so a path with blue edges from U to V, so not a blue path because it's not directed, then the difference of levels, it's just, you just count along these paths the number of times you go direct, I mean, in the good direction minus the number of times you go in the wrong direction. So for example, here, I mean, so you have V, so you do +1, -1, so it's 0, +1, +2, okay? So U and V, the difference is 2 because you go along this path like this, right? But this path is a path of C, so it's a bicolored path, so it's a blue path, but it's also exactly the same red path. So I mean, all of these edges are blue and red, and because we're in J+, they have the same orientation. Okay, but now that we have the same, then we also see that yes, U and V, they have the same difference of levels in the red BFS basically. Okay, so first, I mean, it's a bit technical, but it's very easy to see what happens behind. Okay, so this is the first property, and now the second property, which is okay, also a bit technical to explain, but quite intuitive to understand. What you know that blue path has just shortest path, is that if X is in level I and Y is in level T, so Y and let's say Y +2, yeah, and there is a path of length T between X and Y in G, okay, then P is a blue path. All right, so yes, how do you see it? Well, this is very easy. So what it means from X to be in the level I, it means it's at distance I from S1, okay? And now what does it mean from Y to be at level, let's say I +2? It's because it's at levels at distance Y +2 from S1. But now if you look at these paths, it has exactly the good length. So it's the shortest path between S1 and Y. So every vertex in the middle, they belong to like consecutive levels, right? So that's it. So the path between X and Y that had the good length, it's also shortest path, and actually it's a blue path, right? So again, too technical for what it is, but I mean, I don't see any easier way to say it. Okay, and now we can show the thing that we wanted to show is that if you have a blue path and a bicolored component, so red-blue, then the intersection of these paths and the component is a subpath of P. Okay, so again, it's not very hard, it's just a tiny bit technical. So you suppose this is not the case. So you have this blue path P, and then you have like 2 points which belongs to the component C, and the path in the middle is not a path in this component, right? So this blue path here does not belong to C. So okay, so what's the length of these paths? It's exactly the difference of levels in blue, right? So this is just the definition of a BFS. So let's say these two guys are at distance. I mean, difference of level is 2, and the path here has the right length. Okay. But now, what I said is that the difference of level in the blue levels, because these two guys belong to the same component, it's exactly the same as the difference of level in the red levels. So these guys are distant, they're at distance 2 in the red levels, but this is a path of length 2. So the previous lemma tells us that this is also a red path. So this is a red and blue path, and so these paths belong to the component, okay? And so by contradiction, it's the intersection is the path, all right? Okay, so the first small technicality, and now let me just give you a few other properties of these components, and then we'll be done. And again, it's the same type of argument, is that suppose you have two vertices X and Y, and then you have two paths, P1 and P2. So one is a red path and one is a blue path. Then what I claim is that they're both red and blue. Okay, and again, it's just because if you look at the blue path here, then the difference of levels in blue is exactly the length of this guy. Okay, but by definition of red-blue paths, these are shortest paths. So the red path has exactly the length, which is the difference of levels. So again, it's also a blue path, etc. Right. So a bit technical once again, but very easy to get. And then now that you have this property, we can basically define the main ingredient in the proof. So the main properties about this component. And it will be, again, definition is a bit strange, but we will see what it means. So if suppose you have P1 and P2, which are two paths, so one red, one blue, and they're possibly intersecting, but maybe not. I mean, it doesn't matter for us now. And you have C, a B-colored component, so red-blue component. So what we say is that P1 and P2 are in conflict, okay, on this component C. If you look at the intersection of C, of P1 and C and P2 and C, so this is P2, so yeah, so this is a path. So the intersection of P2 and C, it's a path, so this we just proved, and the intersection of P1 and C, it's a path. And so we say that in conflict is that basically if you can remove these two paths by something that intersect. Okay, so they might not intersect at the beginning, but we say that they're in conflict if they could have been intersected with the same output, so entry points and exit points in this component. All right, so intuitively what it means that if you just tell me, okay, so let's say P1 and P2, they're the solution that we're looking for. And now I just tell you, okay, so the entry point and exit point of these two paths on these components are these 2 points, okay? So then conflict, if knowing this, these entry point and exit points, then there might be a problem, okay? So you have to do something in it. I mean, you have to be a bit careful about what happens here. So this is just what I mean by conflict. And the nice thing about conflicting components, so suppose that P1 and P2 are two paths which are conflicting on C, then the intersection of P1, P2 is empty outside of C. Okay? So literally, it means that P1 and P2 cannot intersect. And here you see that, for example, if you're looking for P1 and P2, and then you're telling me, okay, there is a conflict here. If this is true, then this is very nice for you, because it means that outside this component, then there is no possible intersection. So you can do whatever you want. You just have to check that you can reach S1 from this point and you can reach T1 from this point, okay? So this is what I mean by conflicting components. And this is nice about, and this is what is nice about conflicting components. So how we prove this? Well, it's not very hard. It's just basically the previous thing is that suppose that these two paths, they have an intersection outside this component, okay? So you have P1, P2, and they have an intersection outside this component. But now the thing is that, okay, so they might not have been intersecting, but you know that you can replace them so that they can be intersecting, okay? So you can assume that they intersect. So look at the last vertex X here in this intersection on this component. And now if you look at these two paths, so the X and Y, so you have one path in red, one path in blue, and then the previous lemma tells us that these two paths are both red and blue. So basically it means that X belongs to this component. Okay, so another way to look at it is say that because they have the same lengths, if you want to go from S1 to T1, then you can replace this subpath by this path. All right, and this is a path of the same length, so it's also a shortest path, and it means that this is red and blue. Okay, so Y belongs to the component, and actually we reach a contradiction. Okay, so conflicting components are a bit strange, but if you tell me that basically P1 and P2 are conflicting, then everything outside is fine. Okay, so there is no possible intersection. All right, and here we arrive to the first point is that suppose you're trying to solve like a 2-2 DSP instance, so two colors, two paths, so one red, one blue. And now I tell you, okay, there is a solution such that the P1 and P2, so there is a solution P1 and P2, so that they have a conflicting component. Okay, so if I tell you this, then there is an easy algorithm. And why? Because, okay, if this is the case, then what you will do, you will guess so this component, and then you will guess the entry point and exit point of each of these paths in this component. Okay, and when I mean guess, I mean try everything. Okay. And so you have like n to the 4 choices, but this is fine. And suppose now that you've guessed the right point, so S1 prime, T1 prime, S2 prime, T2 prime. And now what do I say? I say that P1, P2 cannot intersect outside this component. So in particular, it means that any path, any blue path from S1 to S1 prime, and any red path from S2 to S2 prime cannot intersect. Because if they intersect, then you have a red path which intersects, which is conflicting on this component and intersect outside. Okay, so, and then this is what we wanted, right? We wanted to adapt, we wanted to use Fortune an algorithm in the blue setting independently and the red setting independently. And in order to do that, you have to be sure that red and blue paths cannot intersect. Okay. So here it works for every pass except these two. These two might intersect. Okay. This is the definition of the conflicting component, so they might intersect. And here the trick is to say that, okay, so this is a blue-red component. Okay, so every edges are blue and red, and let's say it's G plus, so they have the same orientation in both color. So what it means that this blue path, it's also a red path. Okay, and here the trick that we're going to do, and this will be the one that makes everything works, is that now I think that the path between S1 prime and T1 prime is red. Okay, so now that if I guess these points correctly, I'm exactly in the setting that I said before. So now instead of looking for one blue path between S1 and T1 and one red path between S1 and T2, I have like two blue paths to find, to verify that they exist, and 4 red paths to find. Okay, but I know that no blue path can intersect any red path. All right, so I can apply fortunate algorithm in both cases, and because they cannot intersect, now I can glue them together. Right. So this is the good thing, and this is what happens when you know that the solution is in conflict. Okay, so there is a component where they can intersect. So sadly enough, it's not always the case. Okay, so we have to do something like a bit different to prove the solution, but this is the main idea for 2, and you'll see how we can get up for like 3 and 4, etc. Later. Okay. All right, so we cannot get something so clean because the paths might not be intersecting. So what we will do is we'll define something a bit similar, but also the definition is a bit strange, is that, okay, now you have a blue path and a red path, so P1, P2. We say that P1 does not see P2, okay, if you cannot replace P1 by a blue path that intersects P2. Okay, so it's a bit strange because on one side you only care about S1, T1, and on the other side you only care about, you care about the path, the real path, but this is what it is, and you will see why I define it like this. So we see that P1 does not see P2 if you cannot replace P1 by a blue path that intersects P2. Okay, so that's the so that's the thing. So it's a bit, the type is not very symmetrical, but we do it for this reason, is that now if you have two paths, so a blue path and a red path, we say that they are blind if P1 does not see P2 and P2 does not see P1. So what I mean is that you cannot replace P1 by a blue path intersecting P2, and you cannot replace P2 by a red path intersecting P1. Okay, so this is not possible, and this is not possible. So the definition of blind, it's a bit weaker than what we had before, because before we said, oh yes, so I have a blue domain and a red domain, and there is no edge which can appear in both paths. Okay, so this is fine. So here it's not exactly that, because you have these paths, and then you know that there is a solution to this request, so that the red path can never be used by any of the blue paths between here. Okay, so it's a bit weaker, but actually, it's enough for us to make Fortune's algorithm work in this case. Okay, so instead of solving them both, like the blue things alone and the red thing alone, you have to solve them together, but it's just a generalization of Fortune algorithm. Okay, and so the goal, and this is what I will present you now, is you want to reduce to an instance. Okay, so you have like one blue, one red, for example. So you want to reduce to an instance with more than one path, but now every pair of paths of different colors, they have to be blind. Okay, so it's a bit weaker than what I showed before, but this would be enough. And this is what we want to reduce to. Okay, so how do we reduce to it? Okay, so suppose you have P1, P2, and always here in this case, you have to think about it as like, okay, the solution that you're looking for. So if P1 does not see P2, then you're happy. Half of the job is done because you want that P1 does not see P2 and P2 does not see P1. Okay, so you assume that P1 sees P2. And what we'll do now is we'll just pick the last vertex on P1, okay, so that there is this path to the end, which is blue. Okay, so so you know that there is a path from S1 to T1 which uses the red edges, and so you go, you push it forward. So you go to the last vertex from which it's possible. Okay, and here I look at disjoint path, so this last vertex is not T1, okay, because the path of disjoint. So in particular, if you look at these paths, okay, so the path from the vertex just after X to the end, this path does not see P1, P2. right? Just by definition of X, basically. Yes, because if there is a path from here to here using P2, I mean, some edges of P2, then, okay, this is the contradiction with the definition of X, right? So this part is fine, and then we have to do something for basically what happened here. And so now what we do is we look at P1 prime. So P1 prime is this new blue path that I defined here. So if you look at P1 prime and P2, well, they intersect, so they are in conflict, right? Just by definition of conflict. So what it means that there is this special component, this conflicting component, that outside this component, everything is fine between P1 prime and P2, meaning like the subpaths, they're blind. I mean, they're more than blind, but in particular, they're blind. Okay, so there is a component so that so here, let's say like this is the first point in this component, and this one is the last. So there are several cases depending on the intersection of C with this path, but it doesn't really matter. But what is good for us is that you have this component here. Okay, so it gives you a partition of P1 into like a finite number of passes and a partition of P2 into a finite number of passes, so that now, so this path is blind with P2, this path is blind with P2, and then there's just a problem with here, but this one belongs to the same, I mean, it belongs to a B-colored component. So this was the same thing that we used before for the conflicting case. So to summarize, what we are doing basically is saying that there exists a decomposition of the path P1 and the path P2. So H1 is the path decomposition. So path decomposition is just, okay, you divide a path into a set of subpaths. Such that anytime you take a path in H1 and a path in H2, that either L1 does not see L2, or they belong to the same B-colored component, right? So this, okay, so this part is fine. And so by doing this, we're almost there. We just have to define a new thing, which is also a bit technical, but again, very easy to understand. It's the intersection of two path decomposition. So as I said, a path decomposition is just like you separate your path into subpasses. So it's the same thing as looking at points and then taking all the subpaths with these points. So for example, you have the blue path here, and then you have two path decomposition or path partitions, one defined by this point and one defined by this point. And so the intersection of two path partitions is basically, okay, so here it's like the minimal path partition so that every path of L belongs to both. Okay, so what we do basically is you take the union of these points, so this one, and this one, okay, and this defines you a new path partition with like all the subpaths between these points. Okay, and the good thing about this intersection is two things. First is that you have a bound on the number of points, so on the number of paths, just the sum of these two. And now anytime you take a path in this new partition, so let's say this one, then it's a subpath of both, right? It's a subpath of this one, it's exactly the same path, and it's also a subpath of this one. And if you take this path, for example, it's also a subpath of this one and a subpath of this one, okay? So if you have two partitions H and Q, then you take the intersection, then every path of your intersection is a subpath of the path in both partitions, right? So that's a good thing. And then now that we've defined this, we can prove, basically what we wanted to prove is that given one blue path and one red path, you can partition, so there is a partition of P1 into H1 and P2 into H2, as well as two B-colored components, so that anytime you take one path, one blue path and one red path, then either they're blind, okay, which is what we want, or they belong to the same B-colored component, okay? And how you do this? Well, you do the proof that we wanted to do, meaning that, so what we did before is we say, okay, there is a partition and a component so that none of the blue paths sees the red path, a part of the path in the partition, but there is the same thing. So you have a partition Q1, Q2, so that none of the red path, I mean, all of the red paths do not see the blue path apart from this component. And then if you take the intersection of these two components, because every path in the intersection is a subpath of both, you have the right properties, okay? So again, this is a bit more technical than difficult, but yeah, this is what it is. So again, yeah, so we have this, so we have this very nice result that tells us, which is more or less like the same situation as before, but with a different definition that tells us, okay, if you have a blue path and a red path, then there is a finite, okay, and here it's important that this is a finite number of points, as well as two components, so that outside this component, the new blue and red paths, they're blind, okay, and this is what we want. Okay, so now you can do the proof for the case k equal to 2. You can do the real proof for k is equal to 2. So without assuming that the path has a conflict, basically like this. So suppose you have S1T1, S2T2. Okay, and so now what you do is you guess this partition. So this nice partition into blind path. So you have a finite number of points to guess and a finite number of connected component to guess. And again, you will change the color of the path in these components. Let's say the blue one, okay? So once you've done this, then you know that if you take a blue path here and a red path here, they are blind. And as we've said before, once you have this, you can use fortunate algorithm to solve everything, okay? So this is really how the case k equal to 2 works. Okay, so that's it. And so now in the few times that remains, let me explain you quickly how we go on, starting from this, basically how we can do the case with more colors than 2. And actually we have almost everything. I mean, this trick of changing colors is enough for us to do everything. So what happens? So suppose you have 3 colors now. So green, blue, and red. And so now what you will do is you will, so you know that there is, okay, let's not guess again. So you know that there is like a partition between green and blue, right? So there is a partition between green and blue, and there is like 2 components, but let's say 1. So that's like now all of the green paths that you defined outside of these components, they are blind with the blue path. So all of the blue paths and green, they are blind outside these components. And you have the same thing. So you have a blind partition between blue and red. Okay, so again, outside 1 or 2 components, let's say 1, all the subpaths that you've defined, they are blind between red and blue. Okay, so now once again, what you do is you change the colors in this component. So this component is green and blue, so you change it to green, and this one is blue and red, so you change it to red. Okay, and once you've done this, all the blue paths that remain, they are blind with the paths of other colors. Okay, so intuitively, and here this is where you do induction, is like you can forget about the blue paths that remains because they're blind with any of the paths of other colors. Okay, so now you do induction, and then you look at the set of green paths and red paths all together, and then you do the same thing. And so basically what you do by induction like this is you show that there is a decomposition. So given a green, blue, and red path which are disjoint, which is basically the solution that you're looking for, there is a decomposition of each path into a bounded number of paths. So here the bound depends on f, k, and l. And we want to go into details, but it's easy to see that this will give you a bounded number of steps. So you have a decomposition into bounded number of paths with some possible change of colors. Okay, so and this is really what makes the whole thing works. So that now each pair of paths of different colors is blind. So this is the fine thing. So you had like a green, a blue, a red, and then you say, okay, now, but I can decompose this green into like, okay, 4 green and 1 red paths, and this blue into like some blue paths and some green and some red, and this red into some red path. Okay, and I can decompose them so that now everything is blind. And once everything is blind, you can just guess or try all the partition possibles as well as the colors, and this will give you n to some function of kl, and you can solve the problem using fortune type of algorithm. It's extension of it, basically. Okay. Someone is talking.
बहुत ठंडा हो लेकिन हम सोच लेकिन प्रॉब्लम क्या है तेरा रूम में कि मैंने ये ओवर से ज्यादा ठंडा है.
Okay, so so that's so that's basically the whole proof. Okay, so that as a conclusion, what I present you is this following theorem that the KL DSP problem admits an algorithm into n of f of KL. Okay, so basically XP. And so this was the edge version. The vertex version is almost the same. It's just conflict components are defined a bit more like, yeah, strangely. So it's a bit more technical, but every idea is the same. And so now the question is, okay, can we push this? Okay, so we proved the disjoint shortest path problem admits an algorithm, and then can we go forwards? And remember that, as I've said before, the main, like, the most important thing that remains is trying to find a solution which of the disjoint path problem, which has the minimum length, the minimum sum of the lengths, for example. And so here we can push it a little bit, okay, which is nice, is that we can solve the problem not only when you have a shortest path, but let's say instead of having a path of length, the distance between Si and Ti from, so Pi is a size distance of Si Ti, you can add like a small constant, okay? Let's say Pi has size at most, the distance of Si Ti plus some constant T. And then if you look at this version, then you can get a polynomial time algorithm, but of course there will be a dependency of in T in the exponent. Okay, and how you do this? Well, actually with the generalization that I gave you, it's not very hard. Because if you look at the path, let's say from S1 to T1, which is not a shortest path, but say a shortest plus T, then along these paths, there is at most T edges, which is either not inside the blue edges or not using the grid orientation. But this you can guess. Okay, so for example, let's say that the path that you have, I mean, the solution is a path that uses this edge and this edge. Okay, and this is why it's like distance +2. Then once you've guessed these two, and then you can always try everything, then what are you looking for? Is you're looking for a blue path from here to here, a blue path from here to here, and then blue path from here to here. Okay, so you have more than one blue path, but as I've said, this we can solve. I mean, we know how to do it. Okay, so because of this, we have a polynomial time algorithm for, okay, the case where they're not shortest, but almost shortest, right? And of course, the question, and then here, I guess, ask me later on, but like, can we push this to like get the best solution possible? I don't know. I mean, it seems that it requires different ideas, but I don't know. And again, let me remind you that everything is open for 3, and I believe, I mean, maybe there is, but I've never found one, that even finding an approximation would be interesting. Okay, for k equal to 3. So can we find a polynomial algorithm for the optimal version of it? And then there is another open problem, which is probably more feasible and more related to what we did, is the question of, the directed version. Can you solve the k-disjoint shortest path problem in the directed case? And again, it's open for 3, and it seems to be much harder. And I guess that would be the end of my talk. So thank you very much. Do you have any questions?
Thank you very much, William.
Thank you.
So, any questions? That's time to ask.
Yeah, I don't see anything in the chat.
Maybe I can ask a quick question.
Please.
Thanks very much for the nice talk. I was wondering what you think of the planar case. I mean, the hardness result doesn't transfer, right?
Oh yeah, okay. I was a bit too fast on it. Okay, I don't want to go into detail. So the planar case is this is the Bergen and Kobayashi paper. They reduce they solve the planar case. So basically what they show is that the Schriver algorithm for disjoint paths in planar graph can be adapted to this setting.
Yeah, but this is the XP algorithm, right? So I was asking about FPTness.
That's okay. That's a good question, but so I don't know if their reduction is XP. That's I mean, I don't. Yeah, this is a good question. I don't know if their reduction is XP.
So they reduce it. They reduce it somehow to a disjoint, a planar directed disjoint paths, right?
Yes.
And if I remember correctly, this is FPT.
Yes, yeah, this is FPT. So this is why I said that I don't know how they reduce it. I don't remember how they reduce it. So maybe you can use other result than just ascribe a result, but I'm not sure. I have to check it out. I'm sorry, but I don't know the answer to the question.
Yeah. All right. Thanks.
But I remember I mean, you can look it up in the paper. I remember it was quite short, so probably you can find it in like 2 minutes or something like that.
Yeah. Okay. Thank you.
Cheers.
Any other questions? Comments? Okay, William, then thank you once again. So I clap my hands then.
Thank you, Peter.
Yes, and see you in 2 weeks. Goodbye.
Bye-bye.